Hi, and welcome back to our video series here. In this video, we're going to look at charge. It is a property of the pieces of the atom, and it rules our world in ways that we don't even imagine. Like gravity, it's obvious. You trip, you fall down. You drop something, it falls. Gravity is that it's easy to see, but we don't realize how integral, how important charge is. So charge is a physical property that allows a substance to experience a force when placed in an electromagnetic field. Now, that's the Wikipedia technical definition, and there is so much to unpack here. So hopefully we'll try to get that done. So it is a property of that object. So big objects like a whole balloon can have charge. Okay, but a proton has charge. So the tiniest, smallest piece of matter can also have charge. The quarks also have a charge. Okay, so we can have charge at all kinds of levels of materials. Okay, but it's a property of that material. So a proton and electron are not the same thing, in part because they have different property. Well, completely because they have different properties, but one of those properties that differs is charge. So a proton is positive, electron is negative. That's one of the distinguishing characteristics. So it is a property of that material. It allows the substance to experience a force when placed in an electromagnetic field. So we're going to talk about electric fields first, and then later we're going to talk about magnetic fields. And in more advanced physics, electromagnetic fields are really just the same thing. Okay, they're different aspects of the same phenomenon. And charge creates electromagnetic fields, and charge responds to electromagnetic fields. And so charge is that property that allows the particle to do that. Now, in our math, we use the variable Q. So another Q that we've used uppercase Q to mean heat. Okay, so we're dealing with a different Q. This one's lowercase. Okay, so be careful. Lowercase q is charge. It's measured in coulombs. Okay, named for the scientists who did a lot of work with this. Okay, now 1 coulomb of charge. 1 coulomb of charge holds 6.24 times 10 to the 18th power electrons. What does that mean? That means in 1 coulomb of charge, there are more electrons than there is sand in all the beaches of the world. Okay, so 1 coulomb holds an amazing number of electrons. It's mind-boggling, inconceivable. Okay, charge can be negative or positive, and charge determines which direction the force pushes. So in general, you've probably heard this one before, and it's going to apply for magnetism as well. Like charges repel, opposites attract. Like charges repel, opposites attract. You got to know that. Can't look it up in your notes. You got to know that one. Like charges repel, opposites attract. So let's take a look. So here I have an electron. An electron is negative. An electron is negative, and they're going to repel. In other words, the force is going to push this electron that way and push that electron this way. So they're actually going to push apart. Okay, so if I took 2 electrons, set them next to each other, and just let go, they would push apart. They repel. If I take 2 protons, same thing. A proton and a proton, they're going to push apart. They're going to repel. Now, let's do some opposites. So a proton and an electron, opposites attract. So I take those 2 objects and let them go, and they're going to move towards the center of charge. They're going to move towards each other. So protons and electron, now I switch them around. Doesn't matter which side which one's on. They're both going to attract to each other. Now an electron and a proton have the same amount of coulombs for charge. So they're exactly the same charge. So instead of electron, electron, I could say Q1 and I could say Q2. 2, if those are both negative and negative, they will repel. Repel. And if Q is positive and positive, okay, they will repel. If one is negative and one is positive, they will attract to each other and they will move towards the center. So let's talk about the electric field surrounding a charge. So just by the fact that a charge can, kind of like our potential energy, when I hold my pencil up and then I drop it, it has the potential to drop, and we call that potential energy. Electric field is, in a sense, the charge, like putting out feelers and going, where are the other charges? Okay. And as soon as it senses another charge, then you get the force and it's going to react however Coulomb's law, opposite attract, like repel. Okay. This is called a field because it puts it out there and it will pick up any charge and react to it. So an electric field is the unit of force per unit of charge. So in a sense, we're going to take this idea of what that means is it's looking for another piece of charge. Okay. And how we draw this is we pretend like the charge I'm going to place in here is going to be a positive charge. So if I place a positive, we call it a positive test charge, what's going to happen? Okay. So the force is going to push that way. And the force is going to push that one that way. Okay. If I have an electron and I put a positive charge, which way is it going to go? They're going to go towards each other. Okay. So the test charge itself is going to go away. And that's why we draw these field lines that way. So if I gave you a random charge and I said, okay, you have a positive charge, what's the electric field look like? So field lines, positives always go away and they go from the center of the charge. Okay. Always go away. And you'll notice this, a hint, I always draw the direction that I'm going so that I don't forget. I could draw those lines any direction I want, but I always start at the middle and draw away. Electron goes towards. And this is important because we can actually have thousands of charges and theoretically we could map out the electric field that's created based on that. Okay. So that is positives go away, the field lines go away, negatives, the field goes towards the charge. Now this is for an electric field. Later on, we'll talk about a magnetic field and it's going to be similar yet different. Okay. So positive charge goes away, electric charge goes towards. So now let's look at the electric field of a system of charges. So we've got a negative and a negative. So if they're like charges, what are they going to do? That's right, they're going to repel. Positive and positive, like charges, what are they going to do? They're going to repel. Positive and a negative, opposites attract, so they're going to come together. So notice this, notice their field lines. See how these do not actually connect, do not connect? That's actually part of how we can determine in a complex series of charges how things are going to work just looking at it. So because the lines don't connect, they're going to repel. Here the lines are connecting up and they're going to attract to each other. Okay, so how do we do this? So we always draw, what I do first is I usually always draw first the lines going towards at the beginning. When you're drawing these for yourself, draw the lines going toward, and toward. But just know that because of this other charge, it actually causes the field lines to repel each other, if you can think of it that way. And so they're going to bend away from the other charge. So the field lines are going to bend away from the other charge, but they're still going towards. So this arrow is important. If you're drawing field lines, you've got to show me the arrow. Which direction are these going? So it's going towards the negative, but it's bending away from the other negative, okay? So look here, same thing. It's going to bend away from the other positive, but it's still going away from the charge. It's going away. And you should draw all of the lines when you're doing this, okay? Opposites attract is easier because you always go from positive to negative. Notice this, it's going away from the positive to the negative, okay? So if we covered up the positive part here and just looked at the negative, we could almost draw the lines and they would look the same. And then if we covered up the positive, they would look the same. Just notice that here on this side, what's happening, instead of going out straight, that field line is actually bending towards, it's attracted to the other charge, okay? So it starts to go away, but then it's bent and attracted towards. So this actually, if we drew it all the way, would connect with that one. And then this one would connect with that one, okay? And same here. But it's away from the positive towards the negative. Opposites, they're going to link up. Negatives, they're going to push away from each other, the field lines, okay? Why is this important? What this actually tells us is, like gravity, my ruler doesn't have to be touching the ground to feel the force of gravity. It's going to fall, but it's not touching the ground, okay? It's not touching the earth, but the earth's gravity is still going to pull on it. That's called a field. So this is a field where I have a charge here and a charge here, and they're going to detect each other and they're going to react to each other based on how their fields link up or push away from each other.